So let's talk about differential operators. Okay, so a differential operator, when applied to an image, it returns some derivative. Okay, and we're going to model these operators as filters, as masks, as kernels that are going to compute that image gradient function. All right, and then we're going to threshold this gradient function to select the edge pixels. All of which brings us to the question, what is a gradient? All right, so here you got to go way back in your mind there somewhere for those of you. And I guess I make too little. I mean, many of you are heavily involved in the getting your degree or your courses, and you've been taking all these math courses. If so, I apologize for being so pedantic. For those of you who haven't looked at a calculus course in a while, we're going to have to remind you a little bit about multivariate calculus, okay? And multivariate is when you had a function that was a function of more than one variable. So, for example, an image is a function f or I of two variables, x and y. And when I have functions that are a function of more than one variable, I can take what's referred to as a partial derivative, the derivative in the x direction or the derivative in the y direction. And the gradient is the vector that's made up of those derivatives. So let's take a look at this for images. So I'm going to write this as the gradient of an image, and this is that operator that I'm going to use to show the gradient. In an image, it's just a two-vector made up of the partial of f with respect to x, the gradient of the image in the x direction, and the partial of f with respect to y. Okay? So here's an image, and as you can see in this image, it's only changing in the x direction. So its gradient would be whatever the change is in the x direction and 0 in the y direction. Likewise, here's an image that only changes in the y direction. Now, in this case, I'm talking about, I was drawing the arrow in this way. We can either think of y as going more positive as you go down. We talked about this. Or you can just say that this is the direction of the gradient in the sense that in this direction is where it's getting brighter. Okay? So in this image, my gradient would be 0 partial of f with respect to x, but I would have partial of f with respect to y. And normally, of course, I have change in both direction, and that's the gradient itself. It's the partial of f with respect to x and the partial of f with respect to the y. And it has both a magnitude, how quickly things are getting brighter, and also you can see there's this angle, which is sort of the direction of that gradient. And the gradient of a function is the direction of most rapid increase in intensity, and the magnitude of that vector is how much it's changing as a function of a unit step in that direction. Here we're just expressing all of this mathematically. The gradient is given by the two partials. The direction can be computed by just computing the arctangent. That is, the arctangent of the change in y over the change in x. Computer people amongst you should probably use atan2, so that if the partial of f with respect to x is 0, that your machine doesn't explode. And then we can also talk about the magnitude of the gradient, which is just the magnitude of these sum, and that's telling you how rapidly the function is changing, which of course is clearly going to be related to something to do with edges, because remember we said at edges we get steep cliffs where things change tremendously. So we're going to look for large magnitudes of gradients when we're finding edges.